Okay, so then f prime is decreasing when it has negative slope. So on that stretch. So we could say that f is concave down on that stretch, and f is concave up on those darker blue stretches. And so from f prime, that's how we can get information about f. So what questions do you have so far for me, which is this piece? And then I'll get to the question in the chat window about peaks. So I think the key to this one is remembering that this is a graph of the derivative, and then the function, parent function, is increasing when the derivative is positive. Parent function is decreasing when the derivative is negative. And if we want to talk about concavity, we have to look at the second derivative, which is the derivative of the derivative. So that would be when the derivative is increasing or decreasing. And one thing that I think trips students up is whether you're talking about if the values are increasing or if the slopes are increasing. So really watch your language. When I say f prime is increasing, I'm talking about the values of f are going up. As x is moving in the positive direction, if the y values are also moving up, that's increasing. If the y values are moving down, that's decreasing. Okay, so then there's another question in the chat window about if we have a graph of the original function. I think if I'm misinterpreting this, go ahead and let me know in the chat window. But let's go ahead and have a graph of f of x. This is the parent function. And try to give us some orientation here. So let's see, a slope of 1 might look like this. How do we know where the derivative graph is going to peak? Or how do you know where the graph peaks on the derivative graph based on the original? So I'm assuming the question is about where does the derivative graph peak? But if I'm wrong, let me know in the chat window. And so the way I'm interpreting that is where's the max derivative? Where's the steepest? Steepest slope is the way that I would interpret that. So if we kind of take a look at some tangent lines here, I'm just going to draw a line for reference. That's pretty close to the line y equals x. This is about slope equals 1. And we can actually slide this around if we need to, but we can see that the function has about a slope of 1 there and about a slope of 1 there. And it's basically shallower everywhere else. So we might say that the derivative graph should peak in steepness somewhere in this stretch, and the value would be at positive 1. So it looks like the derivative starts off close to 0, gets steeper, and then these tangent slopes start to get less steep and gets pretty close to 0 again. And then again over here, we're about at a value of 1. And it looks like we might kind of stay at a value of 1. So something along those lines. So you can take a look at the steepness to figure out kind of where the derivative might peak. So this green graph would be the derivative graph. When the derivative is positive, the original function f will be increasing. When the derivative is negative, the original function will be, when f prime is negative, the original function will be decreasing. And we have concave up when f prime is increasing. So it looks like from about here on up, we would have concave up on the original function, and concave down when f prime is decreasing. So whenever this function is decreasing. Right around in here, we might have something else going on. What's going on with the derivative, say right here? What's with the derivative of the derivative? F double prime is equal to what about that point? And this ties in with the web work question. So what can we say about f double prime at this point? I've given you a graph of f prime. I'm asking you the question about f double prime. So I'm asking about the derivative of f prime. Yeah. So if we thought about a tangent line, that tangent line would have horizontal slope. So we say the slope is 0. Okay. And we have f double prime is equal to 0. What's the concavity though before and after? Concavity of f. So f prime is decreasing. So f double prime is less than 0, which implies that f is concave down. And then on the other side, f prime is still decreasing. So f double prime is still negative. So f is still concave down. So this was a possible inflection point because f double prime was equal to 0 at that point, but the concavity doesn't actually change. So there's no actual inflection point there, no inflection point there. Do we have an inflection point? Does f have an inflection point, and how could we know? So remember, an inflection point is where concavity changes. Does this graph of f, sorry, we're not looking at the graph of f. Based off of f prime, can we decide if there is an inflection point? Does f have an inflection point? Let me know in the chat window. Yeah, so if we take a look at this point right here, we have another place where the slope is 0. So f double prime is equal to 0. And we have f prime is decreasing. So f double prime is negative. So f is concave down. But on the other side, f prime is increasing. So f double prime is greater than 0. And so f is concave up. So at this point, we have a switch from concave down to concave up. So we do have an inflection point here. So this is an example of using a graph of the derivative to talk about concavity.
Okay, so if the point that's between two concavity, with concave up or down or up, it's inflection point. What should we call the one that's 0? Yeah.
This one has no
Yes.
name. I call it a possible inflection point because it's a place where the second derivative is 0, but upon further inspection, we realize it's not an inflection point. So I guess you would just call it a place where the second derivative is 0.
I see.
There, like we would say, like this function is neither concave up nor concave down there. Okay, so then somebody was asking a question about web work number 6. So here's the graph for this one, and the questions are: find open intervals where f is concave up, concave down, and find the coordinates of points of inflection. So, so this case, we have a graph of f. So this is not the derivative case that we were talking about. So we have a graph of f, and we're being asked about concavity. Let me double check. Use the given graph of the function f to answer the following questions. Okay. So one way to check concavity is to draw tangent lines. And if the tangent lines are under the graph, then your function's concave up. If the tangent lines are on top of the graph, the function is concave down. So somewhere in here, we go from being concave up to being concave down. And you could try to kind of estimate that with tangent lines, like when your tangent lines go from, like when one tangent line is now suddenly both above and below. So maybe somewhere in here, like here the tangent line is underneath and here the tangent line is above. So that might say that we have an inflection point here. So maybe at 2, we'd have an inflection point. Okay, here's an interesting thing that happens. F double prime doesn't exist because f prime doesn't exist, right? We have a sharp corner. So here's a place where the derivative, second derivative doesn't exist, but do we have a change in concavity on either side? Looks like we're still concave down over here and still concave down over there. So no inflection point at that place. But if the concavity had changed, then we would have to worry about it. What's going on here? Let's call this point, let's see, 1, 2, 3, 4, 5. If x equals 5, inflection point or not? Let me know in the chat window. Is x equals 5? Give me a y for inflection point. Give me an n for not an inflection point. Okay, and the way you want to ask about inflection is, does the concavity change on either side? So what is, let's see, when x is equals to 6, when x equals 6, is f concave up or concave down? Let me know, concave up, concave down. When x is 6, the tangent lines are underneath, right? So we're concave up. And that goes all the way until 5, right? We're concave up from 5 on out. And we're concave down before. So is there a change in concavity at 5? So the concavity is changing from concave down to concave up. And so yes, we do have an inflection point when x is equal to 5. So let me know what questions you have about that. Inflection points, we can basically just think of they're points on the curve where the concavity changes. And since we go from being concave down beforehand to concave up on the other side, we did have a change in concavity there. And again, you could draw your tangent lines, and we see that the tangent lines, like from 4 to 5, the tangent lines would all be on top of the curve. And for x bigger than 5, the tangent lines would all be beneath the curve. What other questions do you have on WebWork 6? This is WebWork 6. I hope I got the right question. Yeah. Okay, so then what next questions do you have? And they can be questions about like overarching topics, can be questions about the homework, questions about web work. Optimization is, again, one of the harder topics. So we really need to make sure we feel really good about intervals of increase, decrease, concave up, concave down, definitions of extreme values, putting this stuff all together. Okay, I can make up a question like I just did. We can work through this. And then maybe this will bring up some questions that you have. So let's do this algebraically. Let's algebraically go through a problem where, in this case, we have a polynomial. We have a cubic x cubed plus 3x squared. We want to find all the intervals of increase, decrease, concave up, concave down. We want to find all the critical points, all the inflection points, and any extreme values. So just want to find everything we can find out about this function using our derivative knowledge. Okay, so start off by telling me in the chat window, what's the first derivative? What's the second derivative? So let me know in the chat window. F prime of x equals what? And f double prime. And the reason I'm starting with the first and second derivatives is because I need to know about critical points and inflection points. And critical points and intervals of increase and decrease, that comes from the first derivative. And inflection points and intervals of concave up, concave down, that comes from the second derivative. So help me out with this problem. Let me know the first and second derivatives in the chat window. Okay, awesome. Okay, how can I find, so finding the intervals of increase and decrease, I want to know where the derivative is positive or negative, because positive derivative corresponds to increase. But it's an easier question to turn it on its head and ask something else. So rather than asking, where's the derivative positive or negative, what's the question that I want to ask? So instead of asking to start, where's the derivative positive or negative, there's an easier question I can ask. And it's tied to critical points, and it's helping us find the boundaries of increase and decrease. So if I want to find all the x values where my function is increasing, that's the same thing as finding all the x values where the function has a positive derivative, and that's hard to do. So it's a lot easier. Good. It's a lot easier to ask, where is f prime neither positive nor negative? And the reason we ask this question is it's usually a smaller subset of answers, and it's pretty easy to find out where f prime is neither positive or negative. What we're asking is, where is f prime either equal to 0, or where does f prime not exist? So what we're trying to do is translate this and reframe this into a question that's easier to answer. So rather than just saying like, what are the extreme values? Let's start by finding intervals of increase, decrease. So let's start by asking, where's f prime 0? Where does f prime not exist? And in this example, because f is defined on all reals, all reals means negative infinity to infinity. This is the same thing as critical points. We only have to worry about a difference with critical points if there's a chance for the function to be not defined, because critical points are in the domain. And this function's domain is all reals, so we're good. So we can ask the same question of what are the critical points? Like that's the same thing we can get away with doing here. So first of all, f prime of x is equal to 0 if 3x squared plus 6x equals 0. So I can factor 3x out. That leaves me with an x plus 2. Is that right? And so I get 2 critical points from this question. Let me know what those are in the chat window. And if I made a mistake factoring, let me know what the factoring mistake is. Go ahead and put the correct factoring in there. Tell me 2x values when the derivative is 0. Okay, good. Yeah, so we get a 0 solution from here, and we get a -2 solution from here. So these are 2x values that make the first derivative 0. Are there any x values where the derivative is undefined? Okay, so because we have a polynomial, in some ways this is going to be a boring example because the derivative is always defined. But you need to show me that you thought about it. So you need to, like, your answer should convince me, hey, I know I need to check for where the first derivative doesn't exist. So I'm going to write a note like, oh, f prime is always defined because it's a polynomial. And that way I know that you know to think about all these things and you're not forgetting to do a bit of it. Okay, so we have 2 critical points. And one way to think about critical points is that they can break the x-axis up into intervals of x values, where on each interval, the function's derivative is either positive or negative. It can't be any other option. So I'm going to put -2 and 0 on my number line. And if you want, you could think of this as an f prime number line, if that helps you think about what we're doing. And we can take track, like this can be a way to summarize our thoughts about what the derivative is actually doing. Now, in between -2 and 0, could my derivative possibly change from being positive to negative or negative to positive? Is there any chance the derivative could change from like positive to negative? In between -2 and 0, could the derivative change from positive to negative? If it can, what has to be true about the value of the derivative at that point? If the derivative is going to change from being positive to negative or from negative to positive, what would have to be true about that derivative? This is a continuous function. The derivative is continuous. So if the derivative is negative on one, somewhere, and then positive somewhere, and we're limiting ourselves to being between -2 and 0, yeah, the derivative would have to be 0 at some point or undefined. And if it were undefined or 0, we would have found another critical point. So the idea is that in between -2 and 0, the derivative cannot change. It is either positive or it's negative. It's either greater than 0 or less than 0. There's no other option. Because the only other options would be 0 or does not exist, but we just algebraically found all the places where the derivative is 0 and undefined. So we can confidently say that on the entire interval from -2 to 0, my derivative is either positive or negative. And then we can confidently say that on the interval from -2 to 0, my function is either increasing or decreasing, but it cannot be changing from one to the other. And that's kind of the key logical piece here. So if I said that the derivative is positive here, what do we know about the value of the derivative at another point? If I tell you the value of the derivative is positive at this point A, what do you know about point B? What's the derivative at point B? It also must be positive. So what this means is you pick your favorite point on that interval as a test value. And if your derivative is positive at that test value, it is positive on the entire interval. If your derivative is negative at that test value, the derivative is negative on that entire interval. So let's pick our favorite value. I like to pick numbers that are easy to plug into a function, and so usually it's going to be like 1 or 0. So maybe we can try -1. And I want to know, eventually I want to know if f is increasing or decreasing, but my stepping stone to get there is I want to know about f prime. I want to know if the derivative is positive or negative at 1. So I'm going to take that -1 because it's on the interval. I'm going to plug it into the derivative, okay? And we can go into the factored form or the not factored form. It doesn't really matter at this stage. Whatever is easiest for you to think about in your head. And I don't really care what the number is. I just need to know, is that number positive or negative? So let me know in the chat window. Is f prime of -1 positive or negative? Okay, we've got 1 vote for negative. Do we have other people agreeing with that? Okay, so this tells me that on this entire interval, f prime is less than 0, which tells me that f is decreasing on this entire interval from -2 to 0. All right, let's pick another test point. Let's pick a test point smaller than -2. And sometimes for me personally, I like to pick big numbers just because sometimes it's easier to see at a glance. So I might do like f prime of -10, but you can pick any number you want. In fact, everyone should pick a different number. I don't know how you're going to coordinate that. Pick a number smaller than -2. Pick your favorite number and let me know, is the derivative positive or negative there? So if x is smaller than -2, is the derivative positive or negative? Pick any number you want. And my hint is sometimes the bigger number you pick, the easier it is. Yeah, so I might see like for -10, I can see that 3 times -10 squared is going to be a really big positive number, like 300. And then 6 times -10 is smaller. So this whole thing should be a positive number. So f prime is less than 0. That tells us that f has to be an increasing function. Guess what's next? Pick your favorite number on the interval 0 to infinity. So just pick any positive number, plug that into the derivative. Are we going to get out a positive or a negative? And again, why am I plugging into the derivative? Because I want to know if the derivative is positive or negative. Okay, good. What questions do you have for me so far? So we have a function. We computed the first 2 derivatives. We asked the important question, where is the derivative neither positive nor negative? So we found our critical points. And do we have enough to write the intervals of increase and decrease now? We can say that f is increasing on -infinity to -2 and 0 to infinity. And we can say that f is decreasing from -2 to 0. How do you feel about those conclusions so far? So we have intervals of increase and decrease, and we have the critical points. Okay, so all the work that we did for critical points and increase and decrease, we can apply that directly to the second derivative instead of the first derivative, and we'll get all the concavity stuff kind of for free. Okay, so I have to make a new page here. Put a W in the chat window if you want me to wait before making a new page because you want to take a screenshot or something. I'll like count to 10 in my head, and if there's no W's, okay, great. And then when you're ready for me to move on to the next page, go and type R in the chat window. So again, you can screenshot this if you want. Okay, so we have, what's our second derivative? 6x plus 6. We need to remember that. So f double prime was 6x plus 6. Okay, so let's find our possible points of inflection. Possible inflection points. And we're going to look, same thing we did before. With the first derivative, we asked whether that was 0 or undefined. So here we're going to ask, where is the second derivative 0 or undefined? Okay, so the second derivative would be 0 when we take 6x plus 6 and set that equal to 0. So what is our possible inflection point from the part of where is the second derivative equal to 0? Let me know in the chat window. Good. That happens when x is equal to -1. Is the second derivative ever does not exist? Sounds a bit weird, but the second derivative always exists. But I need to show the person grading my work that I at least thought about this. I was like, oh yeah, don't forget to check for undefined. Oh, this thing's a straight line, always exists. So we're good there. Okay, so you find the possible inflection points and then you test. So last time we tested with an f prime number line. Now we're going to test with an f double prime number line. It's still an x-axis. It's still like x values, right? And the only point we need to worry about testing is -1. So this -1 splits the x-axis into two intervals, all the values from -infinity to -1, and all the values from -1 to infinity. On each interval, there can be no change of concavity, because if there were a change in concavity, we would have found that in the analysis we just did. So we know that from -1 to infinity, the function is either concave up or concave down, but it cannot change on that interval. From -infinity to -1, the function's either concave up or concave down, but it cannot change on that interval. So now the question in front of us, well, which is it? Is the function concave up or concave down on those intervals? And then is there a change in concavity at -1? So if your first name starts with a letter in the first half of the alphabet, say A through L, pick your favorite point smaller than -1 and tell me what the concavity is on that interval. And if your first name starts with a letter in the second half of the alphabet, say M through Z, pick your favorite number bigger than -1 and let me know the concavity of that interval. So if your first name starts with the letter in the first half of the alphabet, you get to pick a number smaller than -1. Yeah, the second half of the alphabet got the easy thing because you get the 0 interval. Let me know the concavity of your interval, and you're going to test for concavity by plugging into the second derivative, because the second derivative tells us concavity. Okay, so then conclude, what's the behavior of f? What is f doing? Is f going to be concave up or is f concave down? So yeah, we want to know, is the second derivative positive or negative, and then we need to translate that into behavior of f. Okay, so I think the people on the second half of the alphabet get the easier numbers to try. So a couple people tried, we have 0, we have f double prime of 1, but both people got greater than 0, and so we'd say concave up on that interval. I need someone from the first half of the alphabet. Somebody who picked a number smaller than -1. Plug that into the second derivative. Cool. And you get less than 0. So maybe f double prime of -2 would give us 6 times -2 plus 6, which is going to be a negative value. And therefore, the function is concave down. If the second derivative is concave or is negative, then the function's concave down. Cool. So is x equals -1 an inflection point? And I guess we could be nicer. Is the point -1 f of -1 an inflection point? We could name it that way too. So let me know in the chat window. And if you're not sure, you can definitely just say, I don't know. It's great to let me know where we're at. But the question in front of us is, does the concavity change on either side? And yeah, we're going from concave down to concave up. So most definitely yes. F goes from concave down on negative infinity to negative 1 to concave up on negative 1 to infinity. Okay, so we now have listed the intervals of concavity and the inflection points. And I think the only thing left is to talk about extreme values. And I think we can do that on the previous page. So type a W in the chat window if you want me to just slow down and let you write things down. Type an R if you're ready for me to move back to the previous page. So W means wait, R means I'm moving back. Okay, so we did intervals of concavity and we did inflection points, so the only thing left is extreme values. Now, we can do extreme values from the f prime number line, because here, if the derivative is negative, what did I write down? Values let me get away with that. Let's try this again. So down here I wrote greater than 0. For some reason up here I chose not to. So make sure we get that cleaned up. Okay, so if the derivative is positive and then negative, the function's going from increase to decrease. So that tells us we have to have a local, what, max or min? When x is equal to negative 2, we have a local max or min. Let me know. The function goes from increase to decrease. First derivative test says we have a local max. Awesome. And then around 0, we're going from a negative derivative to a positive derivative. So f is going from decreasing to increasing. So if we're going from decrease to increase, we have a local what when x is equal to 0? We have a local min in this case. Awesome. So boom, there's extreme values. So that's one test. That was an example of using the first derivative test. Okay, I want to show you the second derivative test. So put an R in the chat window if you're ready for the second derivative test. Put a W if you want me to chill out and let you write some stuff down. Okay, so we're going to go back to all of our work we did on the second derivative. All right, try to ignore the black writing down there and I'll switch to blue for this. What were the critical points? I'm so distracted by technology. The critical points were, what were they? -2 and 0. Okay. And at those critical points, what was the value of the derivative? Okay, so we knew the tangent lines had horizontal slope. The tangent lines were horizontal, so they had 0 slope. Okay, what is f double prime of -2? So you could tell by our f double prime number line, or we could actually take 6 times -2 plus 6. And what do we get out here? It's going to be -12 plus 6, which is -6, right? So f double prime of -2 is less than 0. So if we have two facts, one, the derivative at the critical point is 0, and 2, the concavity at the critical point is negative, so concave down, we can take a horizontal tangent plus concave down, and that tells us we have a local max. You're taking the horizontal tangent and concave down. This only works if you're exactly horizontal at the critical point, and then you know the function's concave down. Then you have to be at a local max. Okay? And likewise, what is f double prime of 0? Positive or negative? F double prime of 0 is positive. So again, two facts. In this case, we have horizontal tangent line, and then the positive tells us that we're concave up, right? Maybe I could do it this way. Right? Horizontal tangent line plus concave up implies that we have a local min. And that is an example of the second derivative test for extreme values. Okay, so if you want to use the first derivative, then you look for a change, an increase to decrease or decrease to increase. If you want to use a second derivative, you test the exact critical point and you look for a horizontal and tangent line, and then you couple that with concave down or concave up, and that will determine whether you have a max or a min. The second derivative test does not always work, because if you plug the second derivative, plug your critical point into the second derivative and you get 0, it doesn't tell you anything. It's inconclusive. Yes, you will need to be able to use both tests. There will be times when I ask you, do it this way, do it this way. There will be times when I say you get to choose, but I will reserve the right to ask you to explain what would happen if you use the first derivative test? What would happen if you use the second derivative test? Okay, so that's the basic idea behind using derivatives to optimize. So you find the places where you might have a max or min, basically critical points, but then you have to test. And you either look for intervals of increase and decrease and draw a conclusion, first derivative test, or you test the critical points themselves for concavity, concave up, concave down. That's the second derivative test.